Wonderful full stack deep learning people. My name is Harish, and today I'm going to be talking to you about the project that I worked on for this class with another student called Daniel. The project we worked on is called Scancer, which is a breast cancer detection assistant. Now, breast cancer claims very many lives each year, but it turns out that if you can detect the disease early enough, your chances of survival go up quite a bit. Now, if you look carefully at the different kinds of tests and procedures used to diagnose a disease, things like mammograms and biopsies and so on, it turns out that a lot of these different procedures involve quite a bit of human expertise. And this human expertise is not equitably distributed in the world, okay? But it also turns out that the actual act that's happening is a human expert is visually inspecting some sort of scan. So be it a mammogram or be it an MRI or whatever it is, the end result is usually like a person staring at something and trying to diagnose what's going on. It turns out that deep learning based computer vision methods are particularly good at this exact problem. So in the last few years, there have been numerous papers out there from various groups that try to show off how deep learning can help with different aspects of this problem. Now, it turns out there is no central place you can go to, for instance, fetch the best model for, let's say, an MRI. And further, this is not available in a form that you can grab it easily. And even further, it's not available in a form that can be used by an end expert, for instance, a radiologist. So that is what the Scancer project is trying to do. So our goal is to have a sort of collection of deep learning models that cover these different aspects of breast cancer detection. So we happen to be doing this in a PyTorch-centric system. So we imagine this to be a store of models in written in PyTorch, and then model store happens to be in TorchServe. All of this is wrapped up in an API that also happens to be TorchServe. And finally, this whole thing is served up in a sort of an end-user facing application. So for instance, the pathologist could log in and do something useful. So that's the goal of the Scancer project, okay? So what I've described is a fairly open-ended and long-term goal. So let's see what we have working today. To sort of narrow our focus, we decided to focus on just one thing, which is the analysis of lymph node biopsy scans. And what does this mean? So one of the many things you can do to decide whether a person has cancer or not is to take a sample of tissue, which is called a biopsy, from a lymph node, and then stain it in some way, like treat it in some way, and then look at it under a microscope to see, do the cells in it look cancerous or not? And that would end up with something like this. You have like what is called a scan of a slide, and you have an expert that looks at it and marks certain regions as potentially problematic in terms of having metastatic growth. Okay, so this is the problem we chose to focus on, and the one of the many reasons we focused on is that there exists good data, and this happens to be from a grand challenge called the Chameleon 17 and 16 grand challenges. The problem with this data set, though, is that each image is ridiculously large, like, I don't know, hundreds of thousands of pixels across. And further, the actual file size is very large, so each file is, I don't know, many gigabytes large. So even opening one of these and acting on it is quite a difficult problem. So what we actually ended up doing is to work with a simpler data set, which is called the patch chameleon data set, that takes this large file, chops it up into very many small pieces, each of 96 by 96 pixels across, and it's essentially a binary classification problem at this point. So each patch, we have a data set that says, is this cancer or not? So if you look at another talk from my collaborator, Daniel, he goes into some detail about how we use this data to actually train essentially train a binary classification problem. And I'm going to assume that we have such a model, okay? So once we have such a model, and we're going to call it the PCAM classification model, and it happens to look this way, so it's like a classic convolutional neural net model. What we do is we tend to store it in our model store. So before we store it in the model store, we have to make it into a certain specific format. It's called a model archive file, which contains the weights of the model, and it contains this thing called handler, which is essentially what pre-processing and post-processing has to happen before, so when this model is used in production, okay? So when all this stuff is said and done, you can take this model file, a model archive file called an MAR file, and push it to a model store. And so in this demonstration, I'm going to show you that the model is already in the model store, and we're going to look at it. So here is a listing of all the models at the moment in our Scancer model store, and we have just one model, which is the PCAM classification model. Yeah, you can look at some details about it. You can, for instance, look at classification. For instance, you can see that the model was uploaded at a certain date. It has 2 workers that are serving it up. The workers will start at this time, whether the workers use the GPU and stuff. Yeah, so we have some sense that this model has been archived in a suitable format and then sent up into the web. And notice I'm doing everything live with a sort of model store server sitting in the cloud somewhere with SSL and so on. Okay. Now, once this thing is sitting in the cloud, and we can then access it via an API. So here, I'm going to show you 2 test files. So we have 2 test files, one of them 0 being the class without Scancer, and 1 being the class with Scancer. And you can send this file across the wire to our API, another endpoint in the web, again via SSL and stuff. So I send it to PCAM 0, it comes back with 0. I send it to PCAM 1, it comes back with 1. So we have something that's pretty good. We have this model that can do essentially binary classification on a tiny patch of this data set. Okay, so this is great for working in the shell, but what we have is a Django application that sits on top of all this, that you can do essentially the same things we did in the shell. So this application you see here is a combination of things that actually work plus things that are more demonstrative for trying to gather user feedback from particular stakeholders, and we'll get to that in a bit. So coming back to where we were in the shell, we can do things like the exact same thing. The app can tell you, for instance, that the model is being stored, the model is being served with these different parameters and stuff. And further, you can actually test it out in the application itself. So I've given you some sample files. I can even choose a file from my the same files from my hard drive and send them across the wire. And this one is supposed to have cancerous tissue. It says yes, the image you upload has metastatic tissue. You can do the same with the other file. The model is still working, but it will tell you the opposite. Okay, so good. So we have our model, we have it archived, we have it in our model store, we have it served up in our API, and we also have it sort of wrapped by the Django application. Now, the actual problem we're trying to solve isn't these tiny patches, but instead we're trying to solve this overall image that we're trying to figure out whether it's cancerous or not, right? So here we can have some example slides that I've uploaded for just demonstration purposes, and I'm going to go into one of them. So this is how a slide looks. As I was saying earlier, each of these slides are gigabytes large. So the way you even see this showing up on the screen is through like a Google Maps style interface, where as I'm double clicking and trying to zoom in and moving to different regions and so on, the system is sending numerous smaller images across the network. So you can see in my network tab, you can see a crazy number of images coming across the wire as I click into different sections and stuff. Yeah. So it's our expectation that a human expert would come into this system, potentially look at this and then make some sort of diagnosis, right? But to help them along, we've tried to use those patches, and much like in our class, where like in the text recognizer problem, we took this model and we sort of strided it across the sentences and the paragraphs. We've done the same thing over here. We take the model and then we sort of stride it across this larger tissue sample. Unfortunately, this thing, because it's a large image, takes a very long time. So we've kind of done this offline and generate a heat map. And you can download this heat map. And then it's going to be on my hard drive somewhere. So notice that it's ridiculously large. So I'm not even going to open it. So prior to this demonstration, I downloaded the file and sort of resampled it down to like, I don't know, 10 to 20% the original size, so I can please open it and not have it crash my computer while the video is being recorded. So if you look really carefully, you can see that some regions are being highlighted as potentially problematic. And I'm going to zoom in a little bit more, and you can start to see the original squares that go with our classifier. And in this case, I sort of undid the binary classification nest, and I sort of just took the sigmoid output, which goes from 0 to 1, so you can see a nicer color set than just zeros and ones. So if you come back here to this slide, you will realize that it is pointing out something interesting, that the distribution of cells here and the distribution of cells here are quite different, and potentially this is problematic. So it is our goal that, it is our hope anyway, that when these scans come into our system, they can be batch offline sort of figured out, and they can be classified as maybe potentially problematic or not. So when the expert, the pathologist, logs in, they could potentially just say, show me all the high risk points, and they can just focus their attention on that. So if they had a limited amount of time in their day, they can focus on just the bits that are important to them. Okay, so that covers the overall story so far. And where we're going with this in the future is that in order to get more input from actual experts, we're building this out with a proper landing page and so on to try to gather interest from pathologists in particular to see what they have to say about their, like whether it helps them with their workflow, whether we're way off, whether we're actually being useful. And depending on their feedback, we will try to tune whatever we're doing in terms of deep learning for their needs. Okay, so I'm going to go back to this demonstration a little bit to show you something else that we're trying that is not fully working, but it might be exciting just to show off. So notice that when I told you earlier, it is sort of like as I go into different sections, it's generating images. So why not, as it's generating the image, why not try to classify the image on the fly? That's what I'm going to do. Is I'm going to switch to a branch of the code. And restart the system, where now it's going to try to do the same thing. But when I reload this graphic, notice what it's trying to do is as it's loading the different patches, it is passing it through the classification system and trying to do it in real time. Again, as you zoom into this area, you'll realize it's doing the same thing. It's going to mark out that this area is potentially problematic and areas around it are quite green. But again, this takes a little bit of time, so this is part of our work in progress. So coming back, we're trying to demonstrate this to domain experts to see whether they like this or not. And if I've zipped by anything, do not be afraid. Everything that we've done here is open sourced and available on GitHub. We've split this up handily into different repositories for the API, for the web app itself, for one example model that goes into our model store, as well as a bunch of handy-dandy configuration scripts. So if you're interested in anything, like how do we set up tortserve, how does tortserve talk to Django, how do we wrap everything up in a certain way with regards to SSL, termination, all this stuff, everything is carefully documented across all these projects. Okay, so I'm very excited and I'm very grateful for this class to give me the motivation to get started on this project, because I just want to see where this goes in the future. I'm also super excited to see what you guys have done for your projects, and good luck. Okay, thank you. Bye.